In this video, you'll look at how to evaluate polynomial functions and identify general shapes of graphs of polynomial functions. Where are polynomial functions found in nature? If you look at a cross-section of a honeycomb, you see a pattern of hexagons. This pattern has one hexagon surrounded by 6 more hexagons. Surrounding these is a third ring of 12 hexagons, and so on. The total number of hexagons in a honeycomb can be modeled by the function f of r equals 3r squared minus 3r plus 1, where r is the number of rings and f of r is the number of hexagons. Recall that a polynomial is a monomial or sum of monomials. The expression 3r squared minus 3r plus 1 is a polynomial in one variable, since it contains only one variable r. A polynomial of degree n in one variable x is an expression of the form a sub 0 x to the n plus a sub 1 x to the n minus 1 plus a sub n minus 2 x squared plus a sub n minus 1 x plus a sub n, where the coefficients a sub 0, a sub 1, a sub 2, and a sub n represent real numbers. A sub 0 is not 0, and n represents a non-negative integer. So, for example, we could have 3x to the 5th n equals 5. A sub 0 is 3. 2x to the 4th. A sub 1 is 2. And minus 5x cubed, so a sub 2 is negative 5 plus x squared, so the coefficient of x squared is 1 if there's not a number written. There is no x term, so they said a sub 4 is 0, because 0 times x would be 0. And the constant a sub 5 is 1. The degree of a polynomial in one variable is the greatest exponent of its variable. The leading coefficient is the coefficient of the term with the highest degree. So if we just have a constant, there is no x, so it's degree 0. You could write x to the 0, I suppose. So the leading coefficient is the only number we have is 9. This is degree 1, because it's x to the 1. Leading coefficient is 1. We could write a 1 in front of the x if we wanted to. Our degree is 2, so leading coefficient is 3. Degree 3, leading coefficient is 4. So in general, the degree is, written in descending order, is going to be the exponent of your x, and the leading coefficient is the coefficient of that term. State the degree and leading coefficient of 7z cubed minus 4z squared plus z in one variable. If it is not a polynomial in one variable, explain why. Well, it's in descending order even. So this is a polynomial in one variable. The degree is 3, leading coefficient is 7. Again, they gave it to us in descending order, but they gave us the term in one variable. I see 2 variables, so can't do her. And again, it's in descending order, but it needs to be a polynomial in one variable. The term 2c to the negative 1 is not in the form a sub n c to the n, where n is a non-negative integer. And this one is a polynomial in one variable, and I rewrote it in descending order. So our degree is 4, and the leading coefficient is 1. A polynomial equation used to represent a function is called a polynomial function. For example, the equation f of x equals 4x squared minus 5x plus 2 is a quadratic polynomial function, and the equation p of x equals 2x cubed plus 4x squared minus 5x plus 7 is a cubic polynomial function. Other polynomial functions can be defined by the following general rule. A polynomial function of degree n can be described by an equation of the form p of x equals a sub 0 x to the n plus a sub 1 x to the n minus 1, a to the a sub n minus 2 x squared plus a sub n minus 1 x plus a sub n, where the coefficients a sub 0, a sub 1, a sub 2, and a sub n represent real numbers. A sub 0 is not 0, and n represents a non-negative integer. A common type of function is a power function, which has an equation in the form f of x equals a x to the b, where a and b are real numbers, when b is a positive integer. F of x equals a x to the b is a polynomial function. If you know an element in the domain of any polynomial function, you can find the corresponding value in the range. Recall that f of 3 can be found by evaluating the function for x equals 3. A sketch of the arrangement of hexagons shows a fourth ring of 18 hexagons, a fifth ring of 24 hexagons, and a sixth ring of 30 hexagons. Show that the polynomial function f of r equals 3r squared minus 3r plus 1 gives the total number of hexagons when r equals 4, 5, and 6. To evaluate f of r4, every place there was an r, we're going to substitute in a 4. So we have 3 times 16 is 48. Minus 12 would be 36, plus 1 is 37. F of 5, 3 times 25 would be 75, minus 15 is 60, plus 1 is 61. 3 times 36 is 108, minus 18 would be 90, plus 1 is 91. I'm not sure why they call this part B, but whatever. Find the total number of hexagons in a honeycomb with 20 rings. So 3 times 400 would be 1200, minus 60 would be 1140, plus 1, we'd have 1141 hexagons. To find p of y cubed, every place there was an x, I'm going to replace it with y cubed. So power we multiply exponents, so we have 2y to the 12th minus y to the 9th plus 3y cubed. And actually it's easier than what we were just doing because they're not like terms. I can't combine them. I am done. They're getting ambitious this time. They're going to use that b of m function twice. So the first time we want to find b of 2x minus 1. So where there was an m, I'm going to put 2x minus 1. And then we just need minus 3b of x. So where there was an m, I'm going to replace it with an x this time. So I get to FOIL out that binomial. So we've got first term squared, first times second times 2. So minus 4x plus second term squared. And I guess we could combine the minus 1 there, so 2x minus 2. And then I've got, well, nothing really interesting is happening inside those parentheses, so I may as well just distribute the negative. So I'm going to have negative 6x squared minus 3x plus 3. And I can distribute that too. So I have 8x squared minus 8x plus 2. Likes to combine, well, I'm just going to copy down the minus 6x squared minus 1x plus 1, combining the 2x and the negative 3x to get negative 1x, and negative 2 and positive 3 to get 1. And then we can combine our x squareds. 8 minus 6 is 2. And our x's, negative 8 minus 1 is negative 9. And our constants, 2 plus 1 is 3. So this time we got to use the function rule twice, but it combined into one nice final answer. The general shapes of the graphs of several polynomial functions are shown below. These graphs show the maximum number of times the graph of each polynomial may intersect the x-axis. Recall the x-coordinate of the point at which the graph intersects the x-axis is called a zero of the function. How does the degree compare with the maximum number of zeros? Well, degree 0, I have no zeros. Degree 1, 1. Degree 2, a maximum of 2. Degree 3, I get a maximum of 3. Degree 4, a maximum of 4. Degree 5, a maximum of 5. Notice the shapes of the graphs for even degree and odd degree polynomial functions. The degree and leading coefficient of a polynomial function determine the graph's end behavior. The end behavior is the behavior of the graph as x approaches positive infinity or negative infinity. This is represented as x approaches positive infinity, x approaches negative infinity, respectively. So on an even degree function, as f of x approaches positive infinity, as x approaches positive infinity, and f of x approaches positive infinity as x approaches negative infinity. Same thing here, even, so as x approaches negative infinity, f of x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Now on the odd functions, they're doing opposite things. So as f of x approaches negative infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. And same thing on this guy, it's going down. So f of x approaches positive infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. The graph of an even degree function may or may not intersect the x-axis, depending on its location in the coordinate plane. If it intersects the x-axis in two places, the function has two real zeros. If it does not intersect the x-axis, the roots of the related equation are imaginary and cannot be determined from the graph. If the graph is tangent to the x-axis, so it touches in just one place, as shown above, there are two zeros at the same number. The graph of an odd degree function always crosses the x-axis at least once, and thus the function has at least one real zero. The number of zeros in an odd degree function may be less than the maximum number by a multiple of 2. For example, the graph of a quintic function may only cross the x-axis 3 times. The same is true for an even degree function. One exception is when the graph of f of x touches the x-axis. They're going to ask us to describe the end behavior, determine whether it represents an odd degree or even degree function, and state the number of real zeros. F of x approaches negative infinity as x approaches positive infinity, and f of x also approaches negative infinity as x approaches negative infinity. Both ends are going the same direction, so it's an even degree function, and the graph does not intersect the x-axis, so it has no real zeros. In this graph, f of x approaches positive infinity as x approaches positive infinity, and it approaches negative infinity as x approaches negative infinity. The ends are doing opposite things, so it is an odd degree polynomial function, and it intersects the x-axis at one point, so it has one real zero. F of x approaches positive infinity as x approaches positive infinity, and it also approaches positive infinity as x approaches negative infinity. Both ends are doing the same thing, so we know it's an even degree polynomial function, and it intersects the x-axis at 2 points, so it has two real zeros. Wow, they left out the whole end behavior part in the summary. They said the degree of a polynomial function in one variable is determined by the greatest exponent of its variable.